In this lesson, we're going to take a look at a calorimetry demonstration so that we can see how we can use the Q equation to calculate the amount of energy transferred in a process. This is a very common experiment that you might have seen in freshman physics or in first year chem. But let's just take a look at heat transfer between water in a calorimeter and a piece of metal. So I've got my data table set up here. We're going to start off with water and iron. These are the masses for each. We're going to set the initial temperature of water to 20 degrees, iron to 96 degrees Celsius, and the specific heats, these are given to us for these two substances since those are physical properties of the two substances. So let's go to the simulation here. For the iron, we'll just heat it up here. So the metal is going to be heated to 96 degrees Celsius, and then it's going to be dropped into the calorimeter here. If you could get it the right temperature, that would be great. There we go. So metal's being heated, that's at 96 degrees Celsius, water starting at 20 degrees Celsius. So in a calorimeter, usually we have this closed lid. There's a thermometer down into the calorimeter, and there's a stirrer usually to, again, make sure that the heat transfer is occurring evenly between the two substances in contact. And then we're going to wait until the temperature stops changing. In some of these calorimeter experiments, you might see temperature increase, you might see temperature decrease, but again, whenever the temperature stops changing, that's how we know that that heat transfer is done. The assumption is that this temperature, again, we're only actually measuring the temperature of the water, so that's an important thing to keep in mind. This temperature, though, once it's constant for the water, we know that heat is exchanged between two substances that have two different temperatures. So once the two substances have the same temperature, that heat transfer process is going to stop. So that's why we're going to use this number. Notice it's jumping around a little bit, so we'll kind of see what it lands on. Let's do 25.11 degrees Celsius and go back to our chart here. So we'll do 25.11. And again, that's going to be the final temperature for both the water and the iron. Even though we haven't actually measured the temperature of the iron, we know that because of what I was saying about heat transfer, and it will happen until the temperatures become equal. Okay, so this is the equation for heat transfer. So Q, this is not for calculating the heat content of something just at a given temperature. It's got to be involving a temperature change where heat energy is being exchanged. M is mass, C is the specific heat, and then delta T is going to be our final temperature minus initial temperature. So the delta T for water, doing 25.11, which is our final temperature, minus 20.00, and that is 5.11, and that is degrees Celsius. So notice two decimal places on those numbers I'm subtracting. I'm keeping two decimal places in my answer. And so the 5.11 degrees Celsius is what gets fed into here. And the amount of energy transferred. So again, this is a positive delta T, so that means the water gained energy. And so the water has gained 641 joules of energy. And so you could check that in your calculator. For the iron, again, the direction for subtraction, or the order for subtraction, is final temperature minus initial. So again, 25.11 goes first. The iron, though, started at a higher temperature, 96.0. So this does come out to be a negative number, and that is okay, because that tells me that my metal lost energy. And so there's the delta T. Again, I'm going to plug in the negative 70.89 degrees Celsius. Don't want this up here at all. And that comes out to be negative, again, to three significant figures, 641 joules. So that means that the iron has lost 641 joules, the water has gained 641 joules. So this brings up the law of conservation of energy, which is also called the first law of thermodynamics. And basically what we know is that if water gains energy, it has to come from somewhere, and where it's coming from is from the iron. And so they should be equal and opposite signed amounts, equal magnitude amount of energy with an opposite sign. And the iron has a negative because it lost 641 joules. The water has a positive because it gained 641 joules. So this is what we expect. This is the idea behind how calorimetry works. we know that we can measure the temperature change of, usually it's going to be water or a solution, and then from that we can figure out the energy that was gained or lost from our system. So again, in calorimetry experiments, typically the system is going to be our chemicals that we put into water or the chemicals that are in solution in water, but we're measuring the temperature change and using the mass and specific heat for water to help us figure out that energy that came from or went to our system. Let's think a minute about these two questions in purple here. So what would happen to the delta T for water if the mass of iron is doubled and all of the experimental parameters remain the same? So think about what you know about energy, about heat exchange, about specific heat, and what would increasing the mass of the iron do for us in this scenario. So take a minute and think about that, and then let's set that up while you're doing that. So if I'm doubling the mass of the iron, so we're going to reset this, and we're going to select iron again, and double its mass to 40, and everything else stays the same, and let's see what happens. And so while we're waiting for the temperature to increase, we can think about what's actually happening here. So I've heated up my iron. Oh, I forgot to heat up the iron to 96 degrees Celsius. That was silly. Okay, so restarting again, sorry. We've got 40 grams, 96 degrees Celsius. You actually notice before I stopped that the last time, I'd left them both at 20 degrees Celsius. The temperature actually was remaining constant at 20 degrees Celsius. And so that makes sense because I don't have any difference in temperature. There shouldn't be any change in temperature when I put the two things together. So now that I've got it correctly done, doubled the mass of the iron, heated to 96 degrees Celsius as well. What that means is if I've doubled the mass but the same temperature for the iron, that means that I'm actually doubling the amount of energy that the iron has absorbed, because I know that a certain mass absorbs a certain amount of energy and absorbs a certain amount of energy with a certain temperature. So notice my temperature here is around 29.59, and I take a look back at this. So TF equals 29.59, that's degrees Celsius. So think about that, what that means in terms of energy exchange. Notice my final temperature before was 25.11. So notice that it's gone up almost 10 degrees Celsius. So it's almost double the delta T that we saw for the original experiment. Okay, so doubling the mass of the iron, it means that I've got double the amount of energy to transfer to the water. And so again, if I plug these numbers in, we'd see with, roughly double delta T. It's not quite double, but with roughly double the delta T from our original experiment, this number would also double. So that makes sense from what we know about in order to get the temperature of a mass of iron twice that of what we started with, we'd have to have double the energy added. All right, so let's take a look at the second part. What would happen to delta T for water if both the mass of iron and the mass of water were doubled and all of their experimental parameters remain the same? So let's take a look at that. Going to select iron again, double the mass of iron, just like we did in the last example. If I can get it to the right number, that would be great. And up to 96 degrees Celsius, just like before. The reason I selected 96 was because it was easier to drag to. And then we are doubling the mass of water to 60 from 30. And let's see what happens. So again, make your prediction. We saw what happened when we doubled the mass of just the iron. And we doubled the mass of water as well. Well, again, we know that in order for water to change by 1 degree Celsius, or 1 gram of it to change by 1 degree Celsius, we have to add a certain amount of energy. We learned from the last demo that doubling the mass of iron at the same temperature would then allow us to transfer double the amount of energy to the water before. And now notice that this is evened out, and we're back at that same temperature that we were at before for the final T in the very first trial that we did back to 25.11 degrees Celsius. So again, we doubled the mass of iron, we had double the amount of energy available to transfer, but because we had double the mass of water to heat up, we're going to notice that same delta T that we saw in the very first trial, and that's because of those ratios between energy and the mass and temperature of a sample. Let's take a look at another thing that we can do with the calorimeter. If we're trying to solve for an unknown, we can actually, if I don't know what the metal is, we can figure out what the specific heat is for the metal. And so notice I'm going to use these same parameters that we've used before, except we're going to do this for element X. And let's reset this, metal X, and set this to 96. So we can heat this to 96 degrees Celsius. We can put it into our bath here. We can observe the temperature change. So in this case, we're going to know the temperature change for water. We'll know the temperature change for the metal. We know the mass of the water. We know the mass of the metal. And with the information we have, we can calculate the energy that is gained by the water. And now what we know, based on the law of conservation of mass, is that the energy gained by the water must be equal to the energy lost by the metal. So we're getting 25.71, let's say, 25.71 for our final temperature. And again, that's going to be for both of these. Notice I'm not typing in the units in the graph, or sorry, in my table here, because I've got them indicated out here. So that's a nice convenient way to make sure we don't have to rewrite everything. So 25.71 minus 20.00, and so that equals 5.71 degrees Celsius. And so we plug that in, 5.71 degrees Celsius, and that's going to give me 716 joules of energy gained by the water. Now what that means is the energy lost by substance X is equal to 716 joules. So let's plug in what we have for element X, or for metal X. 25.71 is the final temperature minus the initial 96.00, and so that gives us a delta T of 70.29, negative 70.29 degrees Celsius, and again, negative 716, just plugging into the Q equation. So that's Q. We have a mass of 30 grams. We don't know what the specific heat is. We'll leave that as an unknown. And then we now know that it's negative 70.29 degrees Celsius. And if we rearrange and solve, that ends up leaving us with a specific heat of 0.509. Going to keep three significant figures since our joules that we plugged in for Q is limited to that. Now again, for specific heat, so the 716 had joules as a unit, this has grams, this has degrees Celsius. I should probably type this in so you can see it. So that leaves all of these same units on there, and that's what we expect for a specific heat. And so this element X, metal X, we don't know what that is because we don't have a data table in front of us with specific heats of known specific heats of substances. But again, we could try to compare that to a list of known specific heats and see if we could figure out what the unknown substance is. So these are some ways to use calorimetry. Again, it's very important that you clearly identify what's the system, what's the surroundings. If I'm plugging in a mass, it needs to be for the mass that I've measured the change in temperature for, and I need to use that substance's specific heat. And in many cases for our calorimetry work, we are going to be using the mass of water, the specific heat of water, and the delta T of water. And then once we find Q for the water, it's going to be, again, that's our surroundings. The system, the chemicals we're trying to study, that's going to have the opposite sign for the energy that it's gained or lost from the Q that we found for water. So it's very important that we plug in the correct values for the correct substance. So if we've measured delta T, it's going to be for the water in the calorimeter. If we are using water, then and it's delta T, we need to make sure we use its mass and its specific heat. And there you go.